Hi everyone, welcome to Module 6. So Module 6 is acids and bases. So we're going to start off with what are acids and bases. Our syllabus outcome is explore the changes in definition and models of an acid and base over time, to explain the limitations of each model, including but not limited to Arrhenius theory and the Bronsted-Lowry theory. Okay, so let's start. Acids and bases. So acids and bases are two broad groups of chemicals with opposing properties that are encountered in the laboratory and in everyday life. Okay. When we see acids, generally they're corrosive, they taste sour, they neutralize bases, and they turn litmus paper red. Okay, and here's some examples. We've got things like our apple cider vinegar, rice vinegar, white vinegar, citrus, soft drinks, that sort of thing. Bases are also corrosive, but in a different sort of way. They taste bitter. They feel slippery and soapy. So if you put your hands into something like sodium hydroxide, which is a base, it feels like you got soap on your hands. They neutralize acids and they turn litmus paper blue. But what are they chemically? So there are several different scientists over the years that have given us a definition, and scientists then refine and better the definition. So what I want you guys to do, pause the video and research these 5 scientists and their definitions of acids and bases and write it down in your workbook. After that, we're going to go through and discuss what each of these guys did for acid and base definitions. So we have Antoine Lavoisier, Humphrey Davy, Svante Arrhenius, Johannes Nicholas Bronsted, and Thomas Martin Lowry, and Gilbert N. Lewis. So go research those and come back and play the video. So, first one, Antoine Lavoisier. So he proposed that oxygen is the cause of acidity. Okay, he noticed that non-metallic oxides made water acidic, but he couldn't explain why metallic oxides were not acidic. Okay, in fact, a lot of metallic oxides came out as basic. So that was his definition. Humphrey Davy, he came along. He noticed that HCl and H2S gases, when dissolved in water, were acidic. So he proposed that the replaceable hydrogen was the cause of acidity. So that HCl that could be replaced with something like sodium, or the hydrogen in hydrogen sulfide could be replaced with something else. But he couldn't explain why not all hydrogen compounds were acidic. So something like ethanol, not very acidic, not acidic at all. Acetone, not acidic. They've both got hydrogens in them. Svante Arrhenius. So he came along and he observed that acidic solutions conducted electricity just like salt solutions do. Now, his proposition was that an acid was something that dissolved like a salt and released hydrogen ions into the water. So rather than sodium chloride splitting up into sodium and chlorine, HCl split up into H plus and Cl minus. He also proposed that alkalinity was due to the presence of hydroxide ions. So we know hydroxides are basic, something like sodium hydroxide. And when we stick that into water, Arrhenius's theory was that the sodium and the hydroxide split up, and the hydroxide was the cause of acidity. After that, Bronsted and Lowry came along. So these are 2 scientists. They independently discovered this at around the same time, so it was credited to both of them. And they discovered that acids are compounds that donate protons, so aka hydrogen ions, so H plus. So remember, H plus is like a normal hydrogen ion is a normal hydrogen atom is a proton in the middle and an electron on the outside. When it loses that electron, it just becomes a proton. They found that bases are compounds that accept that donated proton. Okay, and this is the theory that we use probably the most. So the Bronsted-Lowry theory. So Acids are proton donators. Bases are proton acceptors. Gilbert Lewis, on the other hand, he thought about it slightly differently. So he defined an acid as something that accepts an electron pair, and a Lewis base is something that donates an electron pair. Now, when hydrogen ions and hydroxide ions undergo neutralization, the H plus ion accepts a pair of non-bonding electrons from oxygen to form water. And so that we can see then that how that oxygen is acting as a base both in Bronsted-Lowry theory, so it's accepting a proton, but it's also donating its electrons to the hydrogen to form a bond. Okay, and so this is probably the most up-to-date theory of acids and bases, but it's the one we don't really use that one all that much, but it is the one that gives us the most freedom, okay, when it comes to acids and bases. But we do prefer to use Bronsted-Lowry. The two that we really have to look at in detail for the HSC are the Bronsted-Lowry definition, which we'll use so much, and the Arrhenius definition, which was, when a acidic salt dissolves, it produces H+. When a basic salt dissolves, it produces OH-. So they're the two that you really have to memorize. So that's what's in the syllabus, but you could be asked about any of the others. So are the following compounds Arrhenius acids, bases, or neither? We'll have a go at that. So remember, Arrhenius, if it dissociates to form H pluses, then it's acidic. If it dissociates to form OH minuses, it's basic. And when it dissociates, if it doesn't form either, then, well, it's neither. So let's have a go at the answers. HCl is an acid. Okay, so it dissociates to form H+. NaOH is a base, so it dissociates to form OH-. Sodium carbonate is neither. Okay, now we know sodium carbonate is a base, but it's not an Arrhenius base. Sodium chloride is not a base at all, or an acid, so it is neither. H2SO4, it's got those H's at the start, so it dissociates to form H+ and is therefore an acid. And copper hydroxide, it dissociates to form hydroxides, so it is basic. Now, our Bronsted-Lowry theory. In the following reactions, are the highlighted compounds acting as acids or bases? Now remember, our definition for Bronsted-Lowry acid is something that donates a proton, and our Bronsted-Lowry base is something that accepts a proton. So here, HCl, it has a proton. On the other side of the equation, it's become sodium chloride. So does it have its proton anymore? Well, no. So it's donated it. So that one is an acid. The second one, we have acetate ion, so CH3COO-. On the other side of the equation, it's become CH3COOH, so it's gained a hydrogen. So if it's accepted a hydrogen, it is a base. The third one, NH3, ammonia. If we look at the other side of the equation, it's become NH4+. I'm sorry, that 4 should be subscript. It's gained a proton, so remember, when something accepts a proton, it is a base. Okay, so this is our summary for today. So remember, acids and bases are present all around us. Our Arrhenius definitions, acids dissociate to form H+, bases dissociate to form OH-. And the Bronsted-Lowry definition, acids donate a proton, bases accept a proton. Okay, so once you've done that, once you've written that down, please go and do the questions in the booklet. And that is all for today. Thank you.